Is it right?
Yes.
Okay, good. So we were talking about the fact that Dirac theory is based on this convention. And the notation we introduced the last time was that gamma mu is defined by the original alpha and beta matrices, and in our basis, yeah, that's right. Looks like this. Psi R is defined to be psi gamma naught. But if you introduce this notation, then everything looks manifestly Lorentz invariant. We have the contraction of lower index mu and upper index mu. It's a little strange because this lower index is really the space-time index of derivative. This upper index is the matrix index given to matrices. But nonetheless, this gamma mu does transform properly as a Lorentz vector. So this combination is indeed Lorentz invariant. So this is the way we can write the Lagrange for the Dirac field. So that's one thing we discussed. Another thing we discussed is that in the case when mass vanishes, then solution for the negative energy, the negative velocity, would lead to this in the limit of no mass. So if you're talking about massless spin 1/2 particle, what you see here is that the negative velocity solution is an eigenstate of the matrix for the gamma 5, which changes the upper two components and lower components into each other. So in this case, gamma 5 eigenvalue is -1 because of this minus sign. And gamma 5 actually turns out to be conserved because if you go back to Dirac Hamiltonian and look at this commutation relation, I mentioned this the last time, P can be factored out. And you just need to compute this, the commutation relation, and then it turns out that they are 0. This is the way I actually confused the K the last time, when I actually didn't write it this way completely. But anyway, so the gamma 5 turns out to be conserved. So this gamma 5 is now given a name called chirality. And chiral is the word that came from apparently Greek word for hand, which distinguishes left from right. And whenever gamma 5 eigenvalue is -1, we call this state left-handed. And obviously, when gamma 5 is +1, that's right-handed, okay?
When I was doing the revision, I don't really understand the motivation of setting up gamma 5 in the first place.
So what you see first is that when you look at the explicit positive energy solutions, it does end up being an eigenstate of gamma 5. But at the same time, because it commutes with the Hamiltonian, this is the conserved quantity, which means you can specify a state with the eigenvalue of gamma 5 together with specifying its momentum at the same time.
But how did we identify gamma 5 as the chirality in the first place?
Well, so by just acting this matrix on top of this solution, then you find eigenvalue -1.
So it is an operator like to observe a state. It's not a spinner.
Yeah, you can even define a chirality operator. Psi dagger gamma 5 psi integrated over space. And this is actually conserved. It commutes with the Hamiltonian. And this is actually based on Newton's theorem. And the conserved current is written this way, which is conserved, just like the electric current. So this is actually based on symmetry when you have usual current, you change the phase of the field. And that actually led to the conservation of this kind of current, it turns out. But when you have actually another symmetry of putting this gamma phi matrix in the exponent, that leads to the conservation of this kind of current called axial current. It's called axial because the parity is odd compared to the normal current. That's why it's called axial current. And so this way, this is a conserved neutral charge. It is the symmetry of the theory. And that leads to the possibility of specifying a state according to this eigenvalue of chirality. Does that answer your question?
Yes.
So that lets me use the idea that the neutrino was a Weyl fermion, which means you keep only this, but you throw away the other chirality, which corresponds to neutrino being always negative velocity, and anti-neutrino being always positive velocity. And this is the way the standard model particle physics has been built. So as long as the particle is massless, I told you last time that this notion of keeping only the left-handed particle and the right-handed antiparticle makes sense, because you can never overtake it and look back and observe the opposite velocity. But if the particle does have mass, then it's not going with speed of light, so you can overtake it. And if you look back, this particle looks like it's going backwards from your reference frame, but that doesn't change the spin. So all of a sudden, it looks like a right-handed particle. So what I started to tell you last time is that experimentally, there was now a discovery of the neutrino mass back in 1998, which now poses an important question. That somehow standard model particle physics doesn't work. We have to change that, at least. And then we will talk about how we might actually change it today, but that is the end of the discussion last time. Namely that what used to be the case is that we believed the neutrino was massless, then having only half the degree of freedom, and ditching the other half. So having only left-handed neutrino and right-handed antineutrino is allowed as long as particle is massless, because then the velocity is a Lorentz invariant quantity. So we don't need to add right-handed neutrino and left-handed antineutrino, so we didn't have to have them. And this is the theory with only chirality -1. So your Dirac field theory, right? Without mass time. And you can put this projection operator that gamma phi has to be -1 to survive. So this is the projection operator to keep negative chirality state but drop positive chirality state. And then we say this is the Weyl fermion. So Weyl fermion is not only that appears in particle physics in the context of neutrino, but this is also what appears in condensed matter physics for the quantum Hall effect. There's something called edge state. The quantum Hall effect is a two-dimensional system with a strong magnetic field applied to it. It turns out that there is an electron state that actually moves on the edge. And this is one dimension in space because you're only living on the edge. So this is actually 1 + 1 dimensional, namely two-dimensional field theory. And this is actually an example of the Weyl fermion, which comes with only one chirality, which corresponds to moving only in this direction, but not in the other direction. So this kind of Weyl fermion does appear also in the laboratory this way. So we do talk about Weyl fermion both in particle physics and condensed matter physics. So in this case, you may have either left mover or right mover. And having only one of them is the case of the Y fermion. If you have a Dirac fermion, you have both. Okay? So the Y fermion appears in both contexts. So that's why we thought neutrino is described by this theory of the Y fermion. But I told you last time that if you look at this experiment of looking for neutrinos produced in the atmosphere from the interaction for cosmic ray, this interaction can produce neutrinos that can go into the water tank where it's detected. And if this is happening there, you can also have exactly the same thing happening on the other side of the Earth. So this is zenith angle theta. This is pi minus theta. And you expect exactly the same number of events as a function of cosine theta. Plus 1 corresponds to neutrinos coming from above. Minus 1 corresponds to neutrinos produced the other side of the Earth going all the way from below. And this is basically the horizon from this direction. And theoretical projection looks like this. In the case of one type of neutrino called electron neutrino, data also looks like this. But for another type of neutrino called the mu1 neutrino, data look actually something like that. And about half of them seem to have been lost. And since something seems to happen on them unknown, that means that it cannot be traveling with speed of light, because if something is going with speed of light, time dilation factor tells you that if something is going with speed of light, time would never pass, clock completely stops, so that object should never experience time. But here we are seeing the phenomena that the neutrinos produced above didn't have time to change into anything on its own, but those produced on the other side of the Earth, they traveled long enough that they didn't have enough time to disappear for some reason, which means they are experiencing time. Therefore, it's not going the speed of light. Therefore, it should have mass. And that's what I told you that towards the end of the lecture last week. And now I'd like to explain to you why mass can give us understanding how neutrinos can be lost. So we'll get into this discussion in a moment. But any questions on this stuff so far? Everything okay? Yes, Kate?
How many kind of neutrinos are there?
At least we know 3 of them. And we'll be talking only about 2 of them here for simplicity. Any other questions? Okay. So how does mass help? As I just responded to Kate's question, there are 3 types of neutrinos we know in nature. They are always partnered to some charged particles, and they are collectively called leptons. And this apparently is also from Greek word talking about light particles, which is just historical. So we used to think that the electron is so light compared to proton. The proton was called wet-ball baryon, which means heavy particle. Electron was called lepton, which means light particle. But these days, we have also discovered one lepton called tau, which is heavier than proton. So the name is totally misnomer now, but just purely historical. So there are 3 kinds of particles, which seem to have totally identical properties in terms of all their interactions and the charges and so on. But their masses are very different. This is 5 MeV. This is 105, and this is 1.777 GeV. So more than 1,000 times heavier than an electron, but they have the same properties as far as we know. So they're sort of, the little brother, the big brother, they have identical faces and they look exactly the same, except for their masses. And each one of them has their neutrino partner, and neutrinos have charge 0. And therefore, they don't interact very much with the rest of us. And only interaction they undergo is gravity. and nuclear weak interaction, like nuclear baby decay. And indeed, that's how it was discovered, namely that neutron would decay into proton, electron, and anti-electron neutrino, and so on. So this is a set of particles called neutrinos. They are very, very weakly coupled up with us. And we would like to write down a Lagrangian for them. So now that we know they must have a mass, and there are three of them. And let's talk about two Dirac fields for nu mu and nu tau. And this then also becomes vector. So this is nu mu and nu tau. I didn't have space for it. And once you actually write a Lagrangian in this matrix form, you realize there's a new possibility, is that the mass is also a matrix. So M11, 12, 21, 22. Now that sounds crazy. We always think of mass as a number, but to the extent you're writing field theory, nothing stops you from writing a matrix mass sum when you have multiple fields involved. And obviously, once you have a matrix, you would like to diagonalize it. And that's something that we can have it from your quantum mechanics class, right? So you can always diagonalize this. And we typically diagonalize the mass squared matrix for the reason you're going to see very soon. You write this with identity matrix, which correspond to common pieces. Using cosine and sine. And this delta m squared corresponds to the difference between two eigenvalues. And theta is just mixing angle when you diagonalize this matrix. So when you rotate your basis by angle theta, then two eigenvalues become m0 squared plus minus delta m squared over 2. Hence, the difference between two eigenvalues is delta m squared. But the eigenbasis of the masses is different from the basis you started out with. And this is called flavor basis, because each neutrino comes together with its partner charged leptons, mu1 and tau. And so difference among these three of them is called flavor, like ice cream. But when you go to the basis where masses are diagonal, you of course call that the mass basis. So it looks very strange, but at least that's possible. And it turns out that having a mass as a matrix was the explanation to disappearing neutrinos. And here's how it goes. So when the neutrinos is produced from a cosmic ray interaction, often they come from cosmic ray proton hitting some nucleus like a nitrogen that produces a particle called pion I mentioned sometime earlier, which is a bound state of upward and anti-downward, which then decays into mu1 and mu1 neutrino. So in this case, this particle decays into mu1, and neutrons produced together with it. Therefore, this is really a partner of mu1 in the flavor eigenstate. And the other one is called tau neutrino. That is definitely not there at the beginning. So your initial state is mu1 neutrino. But now we learn that this should be written as an eigenstate of one mass eigenstate and the other eigenstate. And we also use label 2 and 3 for this by reserving 1 to be similar to electron neutrino state. So we would be talking about this mass eigenstate 2 and 3. So this is the initial state you created. But of course, they now evolve in time because they have now mass in it. And how they evolve in time is given by the energy or Hamiltonian by acting this on it. And let's say all of these particles have momentum p. Then this state would have Hamiltonian eigenvalue after quantizing field and writing the equation, the equalization operator. This requires time dependence by e to the minus I p squared c squared plus m2 squared c to the 4th t over h bar, because it has now mass m2. This state acquires a phase p squared c squared plus m3 squared c to the 4th t over h bar. So they acquire different phases slightly by the difference in masses. So what used to be completely aligned states start to evolve slightly differently from each other in their phases. Then this state is no longer the original mu1 neutrino state, but has the other mixture of the tau neutrino state, which is the orthogonal combination from it. Then this is very easy to work out. What you can do to see the probability of state initially created a mu1 neutrino in flavor eigenstate, but you can ask the question after time interval t, does it still keep, maintain the same state? And you can work this out, namely that for nu2 piece, I have cosine, cosine, together with this phase, with mass m2, and for the nu3 piece, here I have a mass m3 in it. Then when t is 0, phases are just 1, cos squared plus sine squared is 1. So that's 100% in nu mu state. But as time goes on, it starts to differ from the original nu mu state. And because we're talking about tiny masses for relatively big energies, the mass we will be talking about later is smaller than electron volt. Energy of these cosmic ray induced neutrinos are typically in the GeV range. So 9 orders of magnitude bigger, so this is actually 18 orders of magnitude bigger. So it makes sense to do a theta expansion in 1 over PC. Then this becomes PC plus m squared c to the 4th over 2 PC. And this leading piece is common to both, so it's not going to affect anything. So this is actually basically an interferometer experiment, looking at the difference in phases evolving time. So I factor out the common phase, which we don't care. Then I have a piece which goes with mass eigenvalue 2. And 3. And now this starts to differ from 1 as time goes on. So we typically define the probability by looking at absolute square of this whole thing. Then clearly this common piece doesn't do anything. Then I can just work out a little bit of algebra to simplify this expression. And this is called survival probability. Because this is the probability for nu mu to survive as mu mu. But there is a probability that this muon neutrino turns into the other neutrino because of this, which is the tau neutrino. And if you do the algebra and work this out, this turns into this expression. And when you evaluate this argument in units we are familiar with, in electron volt squared, and Pc is energy of the neutrino in GeV, and time the speed of light is the length of propagation times 1.24. So this is order 1. And what you see is that when you're talking about the mass, which actually turns out to be 0.05 electron volt squared in delta m squared, and talking about GeV kind of neutrino, and if you go over hundreds of kilometers with it, then this argument here becomes order 1, and muon neutrino starts to change into tau neutrino. And it's an incredible coincidence that it just so happens that typical neutrino coming from the sky in GeV range, delta m squared happens to be in the sub-electron volt range, and the diameter of our Earth, of our planet, is 12,000 kilometers. So that argument happens to be order 1. And as a result, what happened in this experiment is this. Again, zenith angle plus 1 and minus 1. And if you look at how long neutrino traveled, and if you're looking at cosine theta 1, you are looking straight upwards, and typically interaction happens about 20 kilometer altitude. Then you start to gradually look down towards the horizon. It starts to slowly rise from here to there, but from this point on, it quickly rises eventually to 12,000 kilometers. On the other hand, what this formula is telling you is that as a function of L, survival probability starts with 1. And this also just happens that the angle theta to be nearly 45 degrees. So sine squared 1 is about 1. So it starts to disappear almost completely, reappear 100%, and disappear again. So this is the expected behavior once we know the parameters. So what is going on here is that you start out with 100% muon neutrino, but it starts to oscillate into tau neutrino, and come back to muon neutrino, and so on. And this is what is called neutrino oscillation because of that. So if you hold this behavior to this behavior, that here you don't have much of a distance, so you're in this regime and nothing really changes. But once you actually get to this point, you get into this regime, so it starts to actually disappear. But from this point on, it starts to quickly oscillate like this. And then everything averages out about a half. So as a result, this survival probability as a function of the zenith angle is basically one starts to drop and oscillate like this, and this averages out to be a half. So this is the way you can understand the data I mentioned, namely that data was expected to be like this, but what they saw was something like this. And this is the 50% of what you originally had. And that's the data I was showing. I don't know if I actually showed this to you, but here's the data. Pass this out. And this is the way having a mass of this fermion actually does give you explanation why neutrinos seem to get lost on their way. So it's important that they do sense time. There's a time dependence there because of the mass. It's also important that field theory Lagrangian allows you to write a mass as a matrix instead of just a number. So this is actually mismatched between mass eigenstate and the flavor eigenstate. When you produce a neutrino from an interaction like nuclear beta decay or pion decay, they are produced in flavor eigenstate. But that's not necessarily the mass eigenstate. It's produced as a linear combination of mass eigenstates because of this matrix mass. And indeed, we call this a mass matrix. So that's the way we now understand what happened when the experimentalists saw that the neutrinos seem to be disappearing. Now there's another experiment done at CERN trying to shoot the beam of muon neutrino over 700 kilometers of distance and observe that indeed muon neutrino had turned into tau neutrino, because when you send muon neutrino from an accelerator, on its way it turns into tau neutrino, and when it interacts with some nucleus, it produces this tau lepton, and they could see this decay into some other particles. And this is an incredibly short distance of the order of less than a micron, but they have this incredible device using this nuclear motion to see the particle track within such a short distance. They could actually see it in decaying, so that's why they were sure that what they produce is tau lepton. So they really saw that muon neutrino indeed turns into tau neutrino, not just disappearing, but appearing as a different particle. So this kind of weird thing does happen. And then what we learned is that the neutrinos do have mass, not just mass, they have a mass matrix. And that turned out to be the right explanation for it. And when you actually make this a full 3x3 matrix, it turns out that you also have more complicated pattern of oscillation that involves all three types of neutrinos. And even so, you can even have the possibility that probability of oscillation among neutrinos and antineutrinos may be different from each other, which is yet another example of the violation of CP symmetry. And that's why I'm wearing the t-shirts for CP violation today. Yes?
So why do the elements of the mass matrix depend on theta?
So this is just the mass matrix to begin with. And then you just write it this way without loss of generality by defining the angle that will diagonalize this matrix.
So theta is just some arbitrary angle?
Yeah, they are just arbitrary entities. Of course, we measure them experimentally, but they are arbitrary entities, and we just write it this way so that we can read off the angle of this superposition between two mass eigenstates.
Okay, so it's not the same as the theta in the picture?
No, it's the same. So this theta is not theta. Because we're talking about is this linear superposition of nu mu state with the cosine theta squared, and nu tau state with sine theta squared. So that is this theta coming from the diagonalization of the mass matrix.
But I mean, it's not the same as the one in the picture with the Earth and the
Yeah, that's right. This is the zenith angle. Sorry, I'm using the same symbol. That's why it's confusing. So this is the angle measured from zenith from 0 all the way to pi. Sorry about that. So this is the zenith angle.
Okay.
And that is the mixing angle. Sorry. Is it clear now?
Kind of.
So the only place zenith angle appears in these plots when I say cosine theta from -1 to +1. So this is a zenith angle where +1 corresponds to those coming from above, -1 corresponds to those coming from the other side of the planet.
So, why does it depend on the zenith angle then? Is it just because of the distance it travels through?
Yeah, that's right. So as a function of zenith angle, distance, how much neutrinos propagate, would change like this, from 20-kilometer altitude up there to 12,000 kilometers, which is the diameter of the planet.
Okay, makes sense.
Okay? All right, thank you for asking. Alessandro?
I have a question. Do the masses of the neutrinos, are they different?
We had to measure. We
Okay.
didn't know a priori what they should be,
Okay.
but in the end, we measured that delta m squared c to the fourth is about 0.005 electron volt squared. So it's a tiny, tiny number. The lightest particle we used to know was electron, and electron mass squared is 0.511 million electron volt. So compared to that, this is a really tiny number.
Okay. So, but the masses of like the tau neutrino and the mass of like the mu neutrino are the same or are they different?
But they are different.
Oh, by the,
amount.
okay, okay.
Yeah.
Then where does the mass go when there is a
Yeah,
transformation?
that's a good question. So this measurement is basically looking at the phase differences.
Okay.
So the common piece of the mass would cancel because it's common. So this is the way of measuring the mass squared differences, but not mass squared itself.
Okay.
Sam?
Oh, so my question, I think I understand now. So the theta in that matrix comes from the measurement of delta m squared.
That's right. So now we know it's about 45 degrees,
Yeah.
which is the maximum mixing. And when the mixing angle is less than that, then it doesn't disappear fully. It just disappears only to some extent and come back. And that is what happens for the electron neutrino, which I was involved in this experiment. I think I showed you the last time. So in this case, it doesn't fully disappear because angle is less than 45 degrees. Yes?
So, is mass still conserved here, and how does that work when mass is the matrix now?
What question is mass is conserved?
Is it still conserved, and what does that mean when mass is now?
So if you go to the mass eigenbasis, then you rotate this field by this mixing angle. Then you have two fields with different masses. So in that basis, it looks totally normal. Each species have just particular mass as a number. But that's not the way you produce neutrinos. When you produce them, they are produced in this flagrant eigenstate because that's a result of interaction. And that's not the basis where mass is diagonal. That's why you need to use this kind of interference effect in the end, and they start to oscillate. And that is mind-boggling because one particle oscillates to another particle and come back, but that's indeed what happens because we now know experimentally they not only disappear, they reappear into another type of neutrinos, so they really do transform from one flavor to another. And so this has become the big industry. We really would like to know if the neutrinos violate CP, and there's a big experiment being built in the United States to produce neutrinos at the Fermi lab in Illinois. I'm not good at drawing map of United States, but it looks like something like that. And this is a Fermi lab in Illinois, where you have particle accelerator. Using this accelerator, you smash protons on the pocket that produces neutrinos. Then you have an underground experiment being built in South Dakota, or something like 1,200 kilometers. And they're trying to see this possible CP violation in neutrinos, whether the neutrino and antineutrino oscillate with different probabilities. And unfortunately, this is getting delayed because the cost has ballooned. What used to be $1.5 billion experiment is now more than 3. So now there's a big issue from the budget point of view for the Department of Energy. But anyway, this is something that is happening in the United States. And there are a lot of people at the LBO actually working on this, like Kamdu. And there's also similar experiment in Japan. And there's an accelerator on the West Coast. And again, do the same thing. And shooting it to Super Kamiokande, which I talked about before. And in this case, it's only 300 kilometers. It's a small country. But they will have similar sensitivity on studying this question of CP violation. So there's actually a head-to-head competition in that. So this is actually one of the big things happening in the neutrinos. And the reason why this has become an interesting question is something we talked about, namely, why do we exist? So I told you, when the universe started out the Big Bang, energy of the Big Bang turns into mass. But in that case, you produce particle and antiparticle by the same amount because they always produce in pairs. And I told you if we stayed that way, then eventually they would all meet each other 50-50, they all annihilate with each other 1-to-1, and the universe would have been empty, and you wouldn't be here listening to me today. So what must have happened is that 1 part of billion antimatter particle somehow managed to turn into matter particle. Pretty much all of them annihilate with each other. But when they do, there's a difference of 2 here. So they're all gone except for 2 out of a billion. And this is us, right? We talked about that. But when you ask the question, what could have been an elementary particle that can turn from antimatter to matter? Obviously, electron and positron can never do that because they have different electric charges and electric charge is conserved. But maybe neutrino and antineutrino can turn into each other because their charge is 0, minus 0 is 0. So at least they can turn into each other without violating the conservation law of electric charges. So if you look at the list of all elementary matter particles, neutrino is the only candidate that is capable of doing so. So perhaps neutrinos saved us. It's a superhero. And we've been saved by neutrinos. And that's why we exist. And that's why the stakes have gotten very high. Maybe by observing the CP violation, we might get a hint that the neutrino will shuffle the amount of antimatter and matter, but because neutrino distinguishes matter and antimatter by CP violation, it could have preferred to bring the universe on the matter side instead of antimatter side, and maybe that's how we end up being here today. So that's why these experiments are now being planned and they will be done because of this big stake question, why do we exist? Thank you for waiting.
Isn't there also like a Lepton number?
That's right. So, right. So if this happens, then it actually does violate something called Lepton number. A Lepton number is just a number given to all of these species. And you give Lepton number +1 to these guys. And all of their antiparticle counterparts, you give Lepton number -1. And as long as this number is conserved, then muon neutrino can never turn into anti-muon neutrino and so on. So if this is the possibility, then you need to violate Lepton number, which requires something called Majorana fermion, and we come back to that. So what we used to think is that this is the Weyl fermion with a neutrino always left-handed and anti-neutrino always right-handed. But now that we learned that this has mass, this doesn't work anymore because it's not traveling the speed of light. You can overtake it, and if you look back, this looks like a right-handed neutrino instead. So is this actually a state we have never seen before? Then you add another degree of freedom. You also add another degree of freedom. Then you're back to situations familiar in the case of electron and positron. Then you say this is Dirac fermion. And in that case, Lepton number is still conserved. So that doesn't happen. On the other hand, there is yet another possibility. When you have left-handed neutrino, it's not going with speed of light anymore. You run faster than that. You guys are young, you can probably do this, I can. And if you look back, neutrino is moving backwards. It looks like it's a right-handed particle now. And nobody has seen a right-handed neutrino experimentally. But then you say, wait a second, I have seen right-handed electrically neutral fermion before. That's anti-neutrino. So if you overtake it and look back, what you're looking at is the right-handed anti-neutrino. So in that case, Lepton number is no longer conserved because the way you look at it, it might look like a neutrino, anti-neutrino. That's now frame dependent. But that's a possibility too. And then you call this a Majorana fermion. And the way it works is that you have these gamma matrices. And I did not write it, I'm afraid. Let's see. I did write it. But if you do a basis change of this 4-component spinner, in another basis, you can actually make all of these gamma matrices pure imaginary. In Dirac equation, in this notation, looks like this. And in this basis, because all the gamma matrices are pure imaginary, I times gamma matrices are all real, then this equation is completely real. So then you can require that the field itself is real. And if you do that, we have seen this before. In the case of complex time-Boden field, field was expanded in terms of an annihilation operator and creation operator of particle and antiparticle. But in the case of real time-Boden field, to make sure this is Hermitian, you need to identify B dagger with A dagger so that this is a real field. Then you have lost the distinction between particle and antiparticle. They are the same thing now. In the same way, if you have a Dirac field, the spinor field, an annihilation operator of, let's say, electron, and a creation operator for the positron with two velocity states. But when you impose this reality condition, that's the Majorana fermion, to make it real, this is actually A instead. Then particle and antiparticle are the same particles. So just like in the case of spin zero particle, where you could impose this reality condition and to have the particle and antiparticle being the same particle, which happens to a particle like a neutral pion, you can do the same thing also for fermion, so that when you overtake a neutrino and look back, no wonder you get anti-neutrino, because there's no distinction among them. And that's the case of Majorana fermion. So one of the big questions is, in addition to looking for CP violation, whether neutrinos and antineutrino oscillate with different rates, it's also important to know whether neutrino is Dirac or Majorana. And that's another thing many people in the department are involved in, like Gabriel Revigan. She's mounting an experiment in another underground location in Canada called Sudbury. And they're trying to see if the neutrino and antineutrino can really turn into each other in experimental searches. Unfortunately, that is known not to happen more than once in 10 to 26 years. But no grad student want to wait for 10 to 26 years. So the idea is to collect 10 to the 27 atoms and see if maybe one of them turns into the other one in a year type scale. So that's the way you need to build a big experiment looking for the process called neutron's double Weyl decay. And if that happens, then neutrino can turn into anti-neutrino, and therefore, in principle, it could have reshuffled the amount of matter and antimatter in the universe. So the combination of being Majorana and violating CP is sort of the important evidence that indeed neutrinos might have been our superheroes. Any questions about this? Yes?
Yeah, two things. So going back to Lepton number, I believe that besides being a Lepton number for particles and particles, there's another Lepton number for its favor, right? Like electron number.
There is. So we used to think that electron number is conserved, muon number is conserved, tau number is conserved. But now we have seen electron type neutrino going to muon type and tau type, so it's no longer conserved. So we have seen the parity is violated, CP is violated, time reversal violated, but in addition, we have now seen that electron number is violated, muon number is violated, tau number is violated. And some of them might be still conserved, total lepton number might be still conserved, but if we see this, then even that is not conserved. So the physics has been going through all kinds of new data that shows that there are less and less symmetries and less conservation laws in nature for some reason.
Okay, thanks. And then second question regarding like these neutrinos thing can save us from the particular mechanical matter issue. If like, how do you transform the neutrinos which are converted into matter to the actual matter, like organic matter from which we are made of?
Can we say that again? I couldn't really hear you.
So you said that having like neutrinos can distinguish between matter and antimatter, so that would explain why there is more matter.
Mm-hmm.
But that would explain why there is more matter of neutrinos, not matter like organic matter.
So that's an excellent question too. So it turns out that there is a process which happens in the standard model particle physics that you can change lepton number and baryon number together. And that has to do with another effect in quantum field theory called anomaly. And that's beyond the scope of this course, unfortunately. But it turns out that once you have a difference between neutrino and antineutrino, that can automatically turn into the difference between quark and antiquarks too. So that is actually known effect. It had not been observed experimentally, but theoretically completely well predicted and established. So once you make any difference between neutrino and antineutrino, we are done. You can exist. Okay? So that's the story about Majorana. And I do plan to have one problem in the final exam about Weyl fermion and Majorana fermion. It looks a bit messy in 4 dimensions, so I simplify the problem to 2 dimensions. which is actually relevant to condensed matter physics, because Majorana fermion is also what is talked about in the context of topological insulators in condensed matter physics, where somehow electron manages to lose its charge. Spin 1/2 electrically charged particle now splits into two different particles, one keeping only the charge, the other keeping only the spin. And the one that loses the charge and keeps only the spin is now neutral and becomes similar to neutrino. So in principle, it can become Majorana fermion. And that is what is believed that happens in the topological insulator. So you will have a problem of working out Weyl fermion and Majorana fermion in simpler setting of 1+1 dimension. Okay, now that leaves us into the final subject of QED, quantum electrodynamics. So when we talked about, for example, the 2p state of hydrogen decay to 1s state by emitting a photon, we talked about the Hamiltonian, which is point particle Hamiltonian for the matter, and we quantized the electromagnetic field to deal with the photon. And this was still certainly sort of the mixed bag, right? You're dealing with the particle in quantum mechanics, but you're dealing with the photon in quantum field theory. What we should do, and to make sure everything is Lorentz invariant, is to describe both matter and electromagnetism as fields, quantum fields, to ensure the theory is fully relativistic, namely Lorentz invariant. We haven't done this yet. So what we are trying to do is put everything we have done over the semester together into a single theory of quantum electrodynamics. In the way you come up with this theory, again, only combines everything you have heard during this semester. So to describe matter, we have this Dirac Lagrangian. To describe electromagnetism, we have this Maxwell Lagrangian. The only thing we need to change is to make sure that this theory is gauge invariant, because otherwise electromagnetism didn't make sense. We had too many degrees of freedom. To do so, the only thing we need to change is to change this partial derivative to covariant derivative. That's it. This is QED, quantum electrodynamics. So if you actually write this out more explicitly, so this is the definition of the covariant derivative, right? We have done this already many times. There is H bar somewhere. Then if I actually write this out term by term, and separate this piece out there, the first line is free Dirac field, free photon, and we treat this as a zeroth order theory, Lagrangian and Hamiltonian. And this piece is the perturbation to it, which corresponds to interaction. The reason why this corresponds to interaction is something you know already. Namely that each of this field operator consists of creation and relation operator. So using this term, what you can do is to think about the process where you pick annihilation operator here, you pick creation operator there, and inside the photon field, there is also annihilation operator, and everything looks like an A, so let me just change notation. Maybe I call annihilation operator C. Then you're talking about a process that electron comes in, you annihilate it, and create another electron, and you absorb a photon. So annihilation operator inside here can annihilate the photon. So photon comes in, you annihilate it. Electron comes in, you annihilate it. But you can create an electron, probably in a different momentum. So this term allows you to describe this kind of interaction, that electron can absorb the photon. Just by changing derivative to covariant derivative, you have included this possibility in your theory. But you can immediately see this is not it. Because what we talked about is that the electron is a Dirac field. So in addition to annihilation operator for the electron, it contains the creation operator for the positron. So avoid the classical notation. I'm keeping A and A dagger for photon. I'm using C and D dagger for electron and positron. And psi bar is psi dagger gamma naught. So it contains C dagger and D. Photon field, vector potential, of course contains both annihilation and creation operator for the photon. So they actually 2 times 2 times 2, 8 combinations in it. So you can talk about this process, electron coming in, photon is annihilated. So this is A, C, C dagger. But you can also describe a process where you emit a photon. So electron comes in, emits a photon with this creation operator, and the electron turns into a different momentum mode. So that's already also inside this term. You can also use this using D and D dagger. In this case, positron comes in, and using D inside psi bar, and D dagger inside psi, and annihilation operator inside A mu, you have this possibility that the positron absorbs the photon. So it's written with a different order, but they just anti-commute, so you can change the ordering. So positron is annihilated by this D inside psi bar. Positron is recreated using D dagger in psi. And photon is annihilated by A mu, an annihilation operator. So this is the way positron can absorb a photon. And similarly, for positron to emit a photon, D dagger, A dagger. So this interaction also exists. But this is only 4 so far. There are 8. So what else are there? This uses C inside psi and D inside psi bar, which means electron is annihilated by C, positron is annihilated by D, and photon is created by A dagger. So this interaction exists too. Now you start to see this possibility of pair annihilation of matter and antimatter, which is scary. We should be scared of it because we might get annihilated. Fortunately, we survived. But that possibility indeed does come out in this relativistic quantum field theory. But if you use A instead, you have sort of bizarre diagram. This is DCA, electron and positron annihilate together with the photon. That kind of possibility exists too. And then you know the other processes are basically just the inverse of this. This can produce electron-positron pair. I'm keeping D dagger from psi, that creates a positron. I'm keeping C dagger into psi bar, that creates an electron. And A inside A mu annihilates a photon. So photon comes in, annihilated by A mu, and it leads to the creation of E plus E minus pairs. That's a pair creation. And there's this weird diagram too again, which uses C dagger, D dagger, and A dagger. And that completes the list. So what we did is something very simple. You have known already in the course of this discussion that you only promoted partial derivative in Dirac theory by the covariant derivative. But all of a sudden, you have a theory with interactions in it of 8 kinds in a single term. So that can lead to absorption of photon, the emission of the photon by both charged particle, electron and positron. But also you have these processes of pair creation and pair annihilation between electron and positron. And once you know that these fields are indeed written by these creation annihilation operators, all that has to be done is to follow the rules of perturbation theory. And you can use things like Fermi's golden rule to start calculating things. So that's the idea of QED. Looks like you're raising your hand,
Yes.
Sandro.
In all of these processes, there is also an extra photon, isn't there?
I'm sorry?
Like, there is also an extra photon.
Extra photon, in
Yes,
what sense?
in the sense that in order to annihilate a positron and an electron, don't we need like 2 photons?
That's an excellent question, yes. So you can ask the question whether these possibilities really correspond to a particular physical process. The answer is no.
Okay.
And it turns out that when you have electron-positron annihilating, to conserve energy momentum, going to one photon is not possible. It doesn't conserve energy momentum. It can annihilate into 2 photons. That is possible. So what we can do is to glue these together to come up with a process how electron-positron can turn into 2 photons. So the way we can do this is first, you have electron. An electron will emit a photon that uses this part of the interaction. Then you bring in positron. An electron and positron would annihilate into photon. That is this portion of the interaction. We're using the same term, but twice, to come up with this complete process of E plus E minus going to photons. And just like what we talked about in perturbation theory in an interaction picture, when an electron comes in and emits a photon, you become an electron, but you have wrong energy momentum. This by itself cannot happen. But that's okay as an intermediate state of perturbation theory. We talked about that. So as long as this intermediate state would turn into the state which correctly conserves energy momentum, which happens with the second interaction, it's okay. So that's what we talked about when we developed the time-dependent perturbation theory, right? So here, electron emits a photon and becomes a virtual electron. It doesn't have correct energy momentum, but that's still allowed as an intermediate state in a time-dependent perturbation theory. And second interaction would absorb or annihilate this virtual electron, which had a wrong energy momentum, but end result is the real photon, which does have correct momentum and energy, because end result conserves energy momentum properly. So this process does happen. And you can reverse the order of the two. And that's also a possibility. that the positron emits the photon first, and then that positron is annihilated by the electron, it becomes a photon. Again, this positron is a virtual positron. This is a virtual electron because it doesn't have the correct energy momentum, but that's allowed as an intermediate state. And it turns out that they correspond to just different order in time. And if you remember, the time-dependent perturbation theory had this bunch of time order products in it. So once you have time order product, both of them are already included in a single process. So we normally don't write them separately. We just write this. So this is meant to include both of them summed based on two different time orderings. And because two photons are identical particles, you can also have them interchanged. And all you need to do is sum these two processes. And what I'll tell you on Friday in the last lecture is that once you actually draw a diagram like this one, you know exactly what you're doing because you're using this same operator just twice. But following the same rule we have developed in time-dependent perturbation theory, you just insert this interaction Hamiltonian for initial state, interaction Hamiltonian time t1, interaction Hamiltonian time t2, and f, and integrate over t1 and t2 with a time order product. I hope you remember this formula. Then this time ordering takes care of the two time orderings we just talked about. That's already built in. And because final state contains two photons, you can have these two processes appearing. Then all you have to do is to start with E plus C minus initial state, photon, photon final state. You pick up creation and annihilation operators in this interaction Hamiltonian. And each time you use, for example, creation operator or annihilation operator for electron or positron, that comes together with this solution U and V, which we obtain by explicitly solving the Dirac equation. So you associate U and V whenever you actually deal with electron and positron. Whenever you create or annihilate a photon, the field expanded in a mode contains the polarization vector, epsilon mu. So all of these things end up including polarization vectors and the solution of the Dirac equation. So it turns out that this amplitude, by looking at this diagram, can be immediately written down and this actually turns out to be this transition amplitude. And I will tell you how this is derived on Friday, but it's actually very simple. Whenever you use annihilation operator for the electron to annihilate initial state electron, you look at the field expansion in modes, which contains positive energy spinor with annihilation operator, which I decided to use CP, and negative energy solution, which I decided to use symbol D dagger here. And when you annihilate an electron here using this operator, it always comes with this UP in it. So that's how it appears over here. And the interaction Hamiltonian here contains E gamma mu, and this is actually minus I squared, so that's why I have minus IE, together with this gamma matrix. Only extra thing you need to know is this how you can deal with this energy denominator using the virtual intermediate state. And you can work this out. It turns out to be basically inverse of the Dirac equation. And this is the propagator, which corresponds to the energy denominator in the non-relativistic quantum mechanics. You have another interaction using this term again. And then you need to annihilate the positron. So you use psi bar now instead. And here you can annihilate the positron, which comes with this negative energy solution V bar. And when you create a photon, a mu field at the mode expansion of epsilon mu annihilation operator and epsilon mu star creation operator. So creating a photon always comes with this polarization vector complex conjugated. And because the Lorentz index mu is contracted with the gamma mu, this index of the Lorentz polarization vector should be contracted with the gamma matrix mu. And same for the other photon. And this is the piece where two photons are simply interchanged. So it turns out that once you know this Lagrangian, you immediately know all of these things can happen. And using the tools we have from time-dependent perturbation theory, it turns out that all you need to know to do is to draw a diagram like this, how to connect the initial state to final state using these, what we call vertices with a propagator in between. And once you write down these diagrams, you can immediately translate each of the diagram to specific amplitude, which you can write with all solutions you have already seen before. And this is what is called Feynman diagrams and Feynman amplitude, because Feynman invented this technique. So we will look a little bit more into detail on this on Friday and work out some simple examples with it, like how you can have pair annihilation and creation of particles, how the particles can scatter against each other. We probably look at only these two examples, but nonetheless we will do that, and that will be the end of the course. Okay? Any questions? What does this dead silence mean? Yes?
One question though. Can we describe the, I don't know if it's relevant, can we describe, is the, how to say that? Is the concept entropy applies to this kind of process?
I would say no, because we are not putting any temperature in it. And there's something called thermal field theory, where you can talk about this kind of processes in the thermal bath. It's actually a lot more complicated than this, I have to say. But there is a technique to deal with it too. So you can talk about all these processes happening in a thermal bath. Then you can talk about entropy, free energy, and so on. So that's something you can do with quantum field theory too. Any other questions? Yes, sorry.
The last term, what does that mean by like the ordering? So does that mean first you create or annihilate photons and then?
Yeah, so this ordering is not something you need to be too careful about, because as long as they are different momenta, they anti-commute. And photon operator and electron operator totally commute. So in some sense, this ordering doesn't really do anything. You can freely interchange the order, except that you need to remember the minus signs. So that's why I could freely draw these diagrams without worrying about ordering between creation and relation operators. Yes?
And those diagrams goes from bottom to up?
So when I drew this, I meant the time to go from bottom to top. But people use different way of orienting diagrams. So in this case, I drew the time going that way. So sorry, I wasn't consistent. But anyway, you see the idea. Any other questions? Yes. Right.
Can you explain the definition of left-handed and right-handed again?
Yeah. So the right-handed, left-handed, initially we define this to be the eigenstate of a helicity operator. So that was the initial definition. But when fermions massless, this turns out to correspond to the eigenvalue gamma 5 1-to-1. So this definition becomes the same. When mass is not zero, the gamma 5 is not conserved, so that's not a good quantum number to be considered. But still, helicity is a conserved quantum number, so you can specify the state with this helicity operator.
But I remember that you say that like the left-handed neutrino and the right-handed anti-neutrino all corresponds to the chirality of negative.
That's right,
negative
right.
one.
Right.
So in that case.
Yeah. So here I'm only talking about the particle.
So for antiparticle,
Yes.
you have
For
to.
antiparticle, gamma 5 plus 1 means helicity is actually minus h over 2, and this one is helicity plus h over 2. So they get reversed for antiparticle.
Okay, so the term right and left-handed refers to helicity but not chirality.
That's right. So it turns out that, again, because of CPT theorem, if you have particle which is left-handed, then that also needs to come with the antiparticle that's right-handed, because charge conjugation will change neutrino to antineutrino. Time reversal changes momentum and spin at the same time, so it doesn't change the helicity. But parity changes the momentum but not the spin, so helicity reverses. So as a result of the CPT theorem, left-handed particle should always be accompanied by the right-handed antiparticle. So when you require gamma 5 to be left-handed, we use the notation that refers to particle state. So left-handed chirality would be left-handed helicity particle, but that comes together with right-handed antiparticle.
Yeah, I'm just a bit confused because
Yeah,
you
that is
mentioned
confusing
something like
indeed, right.
chirality means something in Greek, ancient Greek that is
Right.
hand.
Right. Yeah, so ancient Greek people didn't know about the antimatter, so blame them.
Sure.
Any other questions? Okay, see you on Friday.